Namaste, my friend, and welcome back to JEE Physics with Typical Monk. This is class 6, and today we meet one of the most beautiful ideas in all of mechanics, the center of mass. Picture a firework bursting in the sky into 100 glowing fragments, flying off in every direction, and yet one invisible point among them keeps sailing along the exact same smooth path it was always going to follow, as if the explosion never happened. That point is the center of mass, and the law behind it is the conservation of momentum. When David first met a two-body collision, he tried to track every fragment separately and drowned in the algebra, until he learned that one steady quantity, momentum, ties the whole mess together. And here is why this matters more in JEE than in NEET. JEE turns the discrete sum into a continuous integral and stretches every collision from one dimension into two. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the center of mass, the discrete sum for point masses, and the continuous integral it becomes for a real, extended body. Second, how the center of mass moves, carried along only by an external force, and completely blind to whatever happens inside the system. Third, linear momentum conservation and impulse. Both are vectors, and both must be respected component by component. Fourth, elastic and inelastic collisions in one dimension and in two, and the coefficient of restitution that tears them apart. And fifth, variable mass systems, the rocket equation, built by integrating a momentum that keeps changing as fuel burns away. Ready? One idea at a time. Let's lay the 4 bricks we'll build on all class. First, the discrete center of mass, a weighted average of position, mass times position for each piece, added up and divided by the total mass. Second, the continuous center of mass, for a real extended body. That sum becomes an integral, 1 over m, integral of x dm. Third, momentum, mass times velocity, and never forget, it is a vector. And fourth, impulse, force integrated over time, and it always equals the change in momentum. 4 bricks, and today's entire class is built from just these. Look at this picture, because it shows exactly how the sum becomes an integral. For 2-point masses, the center of mass is a weighted average. It always sits closer to the heavier mass. Here, 1 kilogram sits at the start, and 3 kilograms sit 4 meters away. The center of mass lands at 3 meters, 3/4 of the way toward the heavier mass. Now stretch this into a continuous rod. Chop it into tiny elements, each of mass dm at position x, and the discrete sum becomes an integral. The center of mass equals 1 over m, integral of x dm. A uniform rod is symmetric about its middle, so that integral collapses to the obvious answer. Its center of mass sits exactly at half its length. Lisa used to fear the integral until she realized it is just the old weighted average, written for infinitely many, infinitely small pieces. Now the one law that never breaks, no matter how violent the collision. First, the law itself. When the net external force on a system is 0, its total momentum before an event equals its total momentum after. Second, momentum is a vector. Conserve the sideways component and the vertical component separately. Never just add up speeds. Third, impulse ties it together. Force integrated over time equals the change in momentum, and during a collision, the internal forces are equal and opposite, so their impulses cancel out in the total. And fourth, the center of mass agrees completely, because total momentum equals total mass times the velocity of the center of mass. A conserved momentum means the center of mass glides at constant velocity, utterly undisturbed by whatever collision happens inside. Time to solve a full JEE numerical together. Slowly, the monk's way. A ball of mass 2 kilograms, moving at 6 meters per second, strikes head-on a stationary ball of mass 4 kilograms. The coefficient of restitution is 0.5. Find the velocity of each ball after the collision. Step 1. Write down what's given. Mass 1 is 2 kilograms at 6 meters per second. Mass 2 is 4 kilograms at rest, and the coefficient of restitution E equals 0.5. Step 2. Set up two equations, momentum conservation and the restitution equation. E equals the relative velocity of separation over the relative velocity of approach. Step 3. The momentum equation. 2 times 6 equals 2v1 prime plus 4v2 prime, which is 12, and dividing through by 2 gives v1 prime plus 2v2 prime equals. Step 4. The restitution equation. 0.5 equals v2 prime minus v1 prime over 6, so v2 prime minus v1 prime equals 3. Step 5. Solve the two together. v1 prime comes out to 0 and v2 prime comes out to 3 meters per second. The first ball stops completely and the second ball carries away all the momentum, and you can check it. 2 times 0 plus 4 times 3 is 12, exactly what we started with. Now look at these three panels, because they tell the entire story of a collision in pictures. Before, mass 1 carries all the momentum, moving toward a stationary mass 2. If the collision is elastic, both bodies separate afterward, kinetic energy is completely conserved, and the coefficient of restitution is exactly 1. If the collision is perfectly inelastic, the two bodies stick together and move as one. Kinetic energy is lost to heat and deformation, and the coefficient of restitution is exactly 0. But look carefully at all three panels together. One thing never changes across every single one of them. Total momentum is identical, before, elastic and inelastic alike. John once assumed kinetic energy must be conserved everywhere, simply because momentum always is. That single mix-up cost him an entire question. Now sit up straight. These 5 lines are what JEE actually asks, year after year. 1. Momentum is a vector. In a two-dimensional collision, conserve the sideways component and the vertical component separately. Never just add up speeds. 2. The center of mass is blind to internal forces. A collision or an explosion happening inside a system never changes how its center of mass itself moves. 3. The coefficient of restitution, E equals 1, is elastic. E equals 0 is perfectly inelastic, and every real collision sits somewhere in between. 4. Equal masses, one initially at rest, a perfectly elastic collision, the moving mass stops dead, and the stationary one takes off with exactly the same velocity. The velocities are simply exchanged. 5. The rocket equation, B equals U times the natural log of m naught over m, comes from integrating a momentum that keeps changing. Variable mass needs calculus, not plain force equals mass times acceleration. Let us drill the G way. Remember the 4 options. Option A, both statements true, and the reason explains the assertion. Option B, both true, but the reason does not explain the assertion. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, assertion. In an elastic collision between equal masses with one initially at rest, the moving mass stops completely and the stationary mass moves off with the same speed. Reason, for equal masses in a one-dimensional elastic collision, the two velocities are exactly exchanged. Both statements are true, and the reason explains the assertion perfectly. Answer A. Second one, assertion. Kinetic energy is not conserved in a perfectly inelastic collision. Reason, momentum is not conserved in a perfectly inelastic collision either. Pause here, the assertion is true, but the reason is false, because momentum is always conserved when there's no external force, inelastic or not. Answer C. This is the chart that catches Sarah every time. Third one, assertion. The coefficient of restitution can be greater than 1 for a real collision. A reason, E, is the ratio of the relative speed of separation to the relative speed of approach, and for any real collision, it lies between 0 and 1. Check the reason first. True. Now the assertion. A value above 1 would mean the bodies gain kinetic energy from nowhere, which is impossible. So the assertion is false. Answer D. A quick match now. Say each formula aloud before I reveal it. Center of mass, the sum of mass times position, divided by the total mass. Impulse, force integrated over time, equal to the change in momentum. Coefficient of restitution, the relative velocity of separation. divided by the relative velocity of approach. And the rocket equation. V equals U times the natural log of m0 over m0 over m. If all four came to you before the reveal, today's toolkit is becoming yours. Here's a favorite G format. I will read some statements. You silently count how many are correct. Statement 1. In an elastic collision, both momentum and kinetic energy are conserved. Hold your verdict. Statement 2. The center of mass of a two-body system comes to rest after a perfectly inelastic collision, even if it was moving before. Think carefully about what actually acts on this system. Statement 3. The coefficient of restitution for a perfectly inelastic collision is 0. So, how many are correct? Two statements, the first and the third. An elastic collision truly conserves both momentum and kinetic energy, and a perfectly inelastic collision truly has E equal to 0. But the second one falls. With no external force, the center of mass keeps moving exactly as it did before the collision. It never simply stops. Two correct. And the middle one is the trap. Now let me save you some marks. Two myths that trap thousands of students every year. Myth 1. Kinetic energy is conserved in every collision. Just like momentum, it feels natural. Surely if one quantity survives, so does the other. But here is the truth. Only momentum is always conserved when there is no external force. Kinetic energy survives only in an elastic collision and is partly lost in every real one. Myth 2. After a collision, the center of mass changes its velocity, sped up, slowed down, or brought to a stop, depending on the collision. The truth, if no external force acts, the center of mass never even notices the collision. It keeps moving exactly as it did before, elastic or inelastic, gentle or violent. One myth, one full G question. Do not let it be the one that costs you. Time to test yourself, rapid fire, and every answer today is a number. Here is the rule. I ask, you answer in your head before the reveal. No pen, no paper, just what you built today. Question 1. A 1 kilogram mass and a 3 kilogram mass sit 4 meters apart. How far is the center of mass from the 1 kilogram mass? 3/4 of the way, so 3 meters. Question 2. A 10-gram bullet moving at 100 meters per second embeds in a stationary 990-gram block. What is their common velocity right after? Total momentum divided by total mass, 1 meter per second. Question 3. What is the coefficient of restitution for a perfectly elastic collision? Exactly 1. Question 4. In a two-dimensional collision with no external force, what exactly is conserved? Not the speed, not the direction alone, the sideways momentum and the vertical momentum, each one separately. And question 5. The thinker. A rocket ejects gas at 2000 meters per second and burns fuel until its initial mass divided by its remaining mass equals Euler's number. What speed does it gain? The natural log of Euler's number is exactly 1. So the rocket gains exactly 2000 meters per second. If you caught that one, you have truly understood today's class. Let us gather the whole class in one slow breath. The center of mass is a weighted average of position, a sum for point masses, an integral for a continuous body. The center of mass moves only under external force. It is completely blind to whatever happens inside the system. Momentum is conserved whenever there's no external force, and being a vector, it is conserved component by component. Elastic collisions conserve both momentum and kinetic energy. Inelastic ones conserve only momentum, and the coefficient of restitution always sits between 0 and 1. Now, variable mass systems need calculus. The rocket equation comes from integrating a momentum that keeps changing as fuel burns away. In next class, we set this same body spinning, rotational motion, torque, angular momentum, and the rigid body that finally starts to turn. This is where the center of mass gets its own axis to spin around. Do not miss it. And so, my friend, we have met the one point that never lies. It may have looked like just a formula for a weighted average, but understand this. The center of mass and the conservation of momentum are the anchor of every mechanics problem you will ever face. Every rocket, every explosion, every collision G will ever throw at you rests on the one law you learned to trust today. Sarah, David, Lisa, and John all started exactly where you are right now with this one class. Be patient with yourself. Tonight, revise the restitution rule once, slowly. E equals 1 is elastic, E equals 0 is stuck together, and everything real lives in between. One idea at a time, you will crack JEE. Of this, I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you in rotation.